Hi, this is Igor Tkachev, and this is a Nemerle screencast that covers pattern matching and algebraic data types. If we compare pattern matching with what we already know as a C# developers, the syntactically closest C# language construction is the C# switch case statement. So let's start from comparing the Nemerle match operator with the C# switch case statement, but before we start, let me show you just one example. We have two methods here. One is written in Nemerle, another one in C#, and right now you don't need to understand what they do and how it works. Just look at this code, and all you need to know is that these two methods implement absolutely the same logic. The only difference is that the Nemerle code is written using pattern matching and algebraic data types. The C# code is written in the very typical imperative style. By the end of this screencast, you will understand what's going on here and how it works. And now let's switch to our demonstration project and start working on the match operator. I have already some code in this project. This is a C# switch case statement, and now I'm going to modify it. I'm going to convert it to the match operator. Nemerle doesn't support the switch keyword, so we have to replace it with the match keyword. Then we use vertical bar instead of the case keyword. We use this arrow instead of the colon, and we don't need break. Now we have the match operator, this compilable Nemerle code, so we can execute our application and get some result. Okay. This example looks like a switch case, and so far we see only syntactical differences. But the match operator has a lot of semantical differences as well, and this is the first one. Let's change the value of our variable to something different and run our application again. Now we have match failure exception. If the C# switch case statement doesn't have an appropriate case for our value, it just keeps all the cases in the switch statement and continues executing the code right after the switch. Nemerle requires that the developer has to provide all the possible cases, otherwise it generates an exception. But of course we can define a default match clause, the pattern that matches any value, so-called throwaway pattern. Also we call it wildcard or placeholder. Okay, so now we can execute our application, and now we have a little bit different result. The second difference. Let's change the sequential order of our patterns, and also I'm going to restore the original value of our variable. Now let's run the application, and we have unmatched result even if we have an appropriate pattern for our input value. So C# switch case statement ignores the sequential order. The Nemerle match operator doesn't. Another difference. Match operator can return a value. Let's create a new variable and assign the match result to this variable. Our match operator is going to return a string, and we will print this string outside of the match operator. Okay, so now let's run our application, and we have our still a match because we need to add just another pattern. Let's do 2, 2. Let's run it again. Okay. If we look at the type of our new variable, we will see that this is a string type. The computation branches of our match operator have to return values of the same type. So if I change, for example, this computation branch to integer, I'm going to get a compiler error. In this example, we match a value of the integer type. Also, we can match strings, same as in the C# switch case statement. So let's try. Now let's run our application and see it works. Well, we can match numbers, we can match strings, or we can match two values at the same time. But in this case we have to use a little bit different syntax for our patterns. We have to use round brackets. It should be 2 here, and now let's run and see. We have unmatched result. It's unmatched because for the combination of our input values we don't have any consistent pattern. So let's add it. 2 and 1. And now I'm going to change our return values to make it a little bit more descriptive. Okay, let's run it again. 2 and 1. But sometimes, even if we match 2 or more values at the same time, we may want to have a pattern that ignores one of the values. In this case, we can use a wildcard to let the compiler know that we accept any value, for example, for this part of our pattern. We can call it sub-pattern or nested pattern. Let's change the return value and run our application. So we have 2 and any now. So actually we can define either complete or partial patterns. In this example we have 4 patterns and 4 computation branches. But sometimes we need to have just one computation branch for 2 or more patterns, and we can do it in this way. Let's just remove this computation branch, and now we're going to print an actual value of our S variable. Let's do it and let's run our application. We have 2 and 1. So we can match multiple values in one match operator. Sometimes when we have multiple values, we may want to combine them in one variable and use them in this way. In C# we can use anonymous types for that, but in functional programming we use another way to combine multiple values in one variable. We use tuples. Nemerle has a native support for tuples, and now we're going to change our code and play with tuples. Let's define a variable and initialize it. And now we can use it. If we look at the type of this variable, we will see this definition. This is definition of a tuple. If I explicitly define this type, I am going to use this syntax. We're almost done. We have just one little problem. Before we had a separated variable and we printed its value. Now it's a part of the tuple and we need somehow to get it back. Of course we can decompose our tuple and get this value back, but in pattern matching we can define a variable right inside of a pattern and bind this variable to any part of the pattern. So let's do it. We use this syntax to define a variable, and as we have 2 patterns and only one computation branch, we have to do it for both. Also, if we have a wildcard as a pattern, we can use simplified version of the syntax. We don't need this. So it means that for this pattern, we check that the first field of our tuple equals 2. The second field can have any value, but we need this value to be bound to the variable s. Let's run it. We have 2 and 1. It works fine, but still it's not what we want. In our original code we had a different result, if you remember. We had 2 and any. So let's implement this logic. We can do it using the with keyword. We use this syntax, and now we can define any variable and we can assign any value to this variable. Let's run it again, and now we have exactly what we need. Just one more feature while we are here. Sometimes we may need to define an additional condition to our pattern. For example, let's define a variable y equals 5, and now we're going to print 1 and 1 only if this variable equals 5. We need to use when keyword, we call it guard, and now we can define any condition. Okay, let's run it. We have 1 and 1, and if we change the value of this variable, we are going to have an unmatched result. Okay, we're done with this example, and now you have an idea what the pattern matching is and how it can be used. This is not everything it can do. We didn't even discuss the algebraic data types, and now it's a good time to start this discussion. In different languages, this type may have different names. Algebraic data type, variant in Nemerle we use this name, or discriminated union if F#. This all the same things, just different names. In Nemerle we use the variant keyword to define an algebraic data type. I'm going to remove all these things, we don't need it anymore. A, and now I'm going to define the options X, Y, and Z. The option Y is going to have a couple of fields. Field 1 of the integer type and field 2 of the string type. I just created a variant. Now we can create an instance of this data structure. Let's do it. Let's define a variable. You remember we don't use new keyword from Nemerle. And one more variable, y and y. So if I define fields for my option, the Nemerle compiler automatically creates a constructor for these fields. So now I have to provide values for these parameters. One and test. Okay, I just defined a variant, I just defined a Nemerle algebraic data type, and now I want to show you the internal implementation of this data structure. I have another project in my solution. This is a C# project, and this project has a reference to our Nemerle application. So we can use types defined in our Nemerle application. We can use them from C#. But if we want them to be available from C#, they must be public, of course. So now let's create the same data structure, but let's create it from our C# application. And we need to change it, of course. And now we can see what we have. A is just a class, Y is an internal class, and we can see the constructor with the two fields. Now let's decompile this code and see what we have inside. This is a class generated by the Nemerle compiler. As you can see, it has a lot of internal compiler chemistry, so let's copy it to our C# application and clean it up. Let's see what we have. When we define a variant, the Nemerle compiler generates an abstract class for the variant. For every option, it generates an inner class that is based on our variant class. If we define option fields, the Nemerle compiler generates those fields and it generates an appropriate constructor. So actually we have a flat data structure, we have a flat hierarchy with the same base class, which is variant. From C#, variant and variant options look like classes, they behave like classes, and actually they are classes. If a variant is a class, then all the class features are available for variants. For example, we can use inheritance. Let's define a new class B, and now we can use it as a base class for our variant. We can define a new method right here for our option, for example, and let's return any number. We can override existing numbers. We can define properties. Our variant class is a base class for our options, so we can use this property from our options. Or we can create a new method, virtual method, and now we can override this method right here. So all the class features are available. Okay, this is a variant, this is a Nemerle algebraic data type. Now we know what it is, we know that a variant is just a class. Of course, in general, a variant is an abstraction, and in different languages the internal implementation can be different. But we look inside of the generated by the Nemerle compiler code, and we know how it's organized from the inside, at least in this language. We don't know only one thing. Why do we need it? What can we do with that? We can do a lot. We can use pattern matching to manipulate this data structure. We can analyze it, we can decompose it and find some patterns. Now let's play with this data structure. Let's play with the pattern matching and algebraic data types. Firstly, I'm going to define a new variable. The current type of this variable is a.y, I need a, so I will pretend that I have no idea what the actual type of this variable is. So now we can match it. We will match it for the actual type, and then we will be able to print it. Now we can execute our application and see that we have y. Yes, we have y option here. We can recognize it and print this value. Okay, so it works. But we have very simple patterns. Let's complicate them and add option fields into our pattern matching expression. We can do it in this way, and let's print something like y with parameters. Okay. We don't have to specify the variant name. We can, but we don't have to. So I delete it, and now I can run my application again and see that we have this result. So this pattern works. Now let's change this value and run it again. Now this pattern doesn't work. This one works because we have different values. They don't match anymore, but still we have y, and that's why this y works. Okay. But we can ignore this parameter, we can ignore it at all, and we use wildcard to let the compiler know that we actually don't care what we have here. Now if we run it again, we see that this pattern works again. Variants can be recursive. Let's define a new field A of the A type. So our field can be any of these types, X or Y or Z. And now let's create the instance of this data type and run our application. We have Z, so this pattern works, and now we are going to try to recognize this pattern. Let's print something like Z, Y, and let's run our application again. We have this result, so we can recognize patterns even like that. Variants can be recursive, patterns can be recursive, so we can analyze very complicated data structures even if they are recursive. We can play forever with the patterns, but it's not going to help us understand the real power of the pattern matching and algebraic data types until we use it in a more or less real project. I have another demo in my solution, and right now we are going to work on it. This is a small part of my real project. In this project I work with SQL a lot. I have an input data structure which is system.link.expressions. I translate this data structure, I transform it, and finally I generate an SQL code. But at the middle of this process I generate a data structure that represents my SQL. So I can analyze it, I can transform it, I can optimize it for different databases, for example. So I can manipulate this data structure before I generate my final SQL. And in this file we can find some types that represent my SQL. In this example I don't have representation of the top level of the SQL, like select clause, from clause, where clause. I have representation only of the expression level. We have here expressions, predicates, and values. For example, we have a variant that represents an SQL expression. A table field is an SQL expression. This is table field. Binary expression. Binary expression, this is binary expression. It has two expressions and one operation, like subtraction, multiplication, addition. Function, this is function. Parameter, we don't have example here. Constant, this is a constant. Condition. Condition is a predicate. A predicate is an expression that returns a Boolean value, like true or false. And we have a variant that represents our predicate, SQL predicate. Predicate can be not, and, or, compare. For example, compare has two expressions and one operation. And as you can see, this data structure is recursive. Also, we have a representation of our SQL value. The SQL value variant represents values for primitive .NET types. Also, I prepared a method, optimize method, we are going to work on. We are going to optimize our SQL expression. We need to implement a few algorithms like this. For example, this is a constant folding. It implements a logic. When we have a binary operation plus operation of two constants, we can summarize them before we generate a final SQL. So we will recognize this pattern that we have this situation binary plus operation of two constants, and we will transform this expression to something different. If we can't recognize anything, we will just return an original expression. And we have test method here. It's very simple. For example, for our constant folding algorithm, I created data structure. This is a binary plus operation of two constants, and we're going to transform this data structure. We're going to optimize it, and I call our optimize method. And if it returns the same reference as our original expression, then we are failed. If it returns something different, we are fine. Very simple, but it's enough for a demonstration. And I have tests for other algorithms. So now let's call these tests from our main method. Optimizer test. Also, we don't need this. Now let's call our application and see that all our tests are failed. So now we can start working on our algorithms. Our first algorithm is the constant folding. To implement this algorithm, we need to check that our input expression is a binary summary operation of two constants. Let's define a new pattern, and we need to check that this is binary. And just for now, I'm going to return an original expression. Later we will replace it with some transformation. So we have a pattern. It's not complete yet, but we can test it. Let's add a breakpoint and run our application. Okay, we stop here, so it means that we have a binary expression. Yes, this is binary expression. We have some parameters here. Let's continue executing, and of course we're going to fail because we didn't complete our algorithm yet. So let's complete it. Next step, we're going to check that this is a binary expression and this is a summary operation. I just ignore operands, so I use wildcard for that. We can execute our application again and see that it works. Next step. We're going to specify our operands. This is constants, so we just define that we expect constants. Next step, let's define the types of our constants. 32. And finally, we are going to decompose our data structure and get these values of our constants. 2. Okay, now let's return some transformed expression. Now we can implement our summary logic. Let's run it now. We see that this test worked before it was failed. Now it's okay, and we optimized our expression. Before we had 10 plus 20, now we have 30, just one constant. So we recognized, we found our pattern, and we transform it and return more optimized expression. Okay, let's work on another one. Now we need to implement subtraction. It's easy. We're just going to duplicate our code and implement a little bit different logic. Let's run it. Okay, this pattern works. Again, we had 10 minus 20, now we have minus 10. Okay. We can do the same for multiplication, but multiplication is a little bit more interesting because we have special cases, like we can multiply by 0 and then we return 0. Let's implement this logic. But in this case, we don't care what we have as a first operand, so we can just ignore it. I can use wildcard to do that, and now we can return 0. So we multiply by 0 and we can return 0. But in this case, we can return existing part of our expression. We have it already. We have it as a part of our input expression. So we can, you remember, we can introduce new variable, and bind this variable to the part of our expression, and then we can return it. So let's do it. Okay, let's try. Okay, now it works. So 10 multiplied by 0 is 0. Next algorithm, we multiply by 1, and in this case we return first operand, first expression. Let's remove this. Let's run it. We see it works. Okay, now we multiply 10 multiplied by 1 is 1. And as you can see, we have the same computation branches here, so we can remove one of them. We can do it in this way. Okay, we have just one more algorithm to implement, and this is a not predicate. If we have not predicate of not equal operation, of not equal comparison, we can return equal comparison. So if it's not equal, we can say that this is equal. Okay, let's implement this logic. Now we can execute our application, and we see that everything works just fine. Actually, we're done with this example. We implemented all our algorithms, we defined all our patterns, and I forgot to mention just one little detail, syntactical detail. As you can see, we don't use match keyword in this method. If a method body consists of a single match operator, we don't have to specify it. We can use this syntax, we can skip the match keyword, and we don't need braces. Now let's get back to the slide we saw at the beginning of the screencast and discuss it in more details. As you see, we have here our latest algorithm we implemented a couple of minutes ago, this optimization of the not predicate. If it's not equal, we recognize this pattern and transform it to an optimized expression. The C# method implements the same logic. The Nemerle method uses pattern matching and algebraic data types. The C# code is written in the imperative style. Now let's compare these implementations and see what's going on here. Let's look at the first pattern condition. I call it pattern because patterns are recursive, and I can call it sub-pattern or nested pattern, but I will say just pattern. When we define this pattern, we tell the Nemerle compiler that we expect our input parameter expression to be an SQL expression dot condition. We expect this type. If we look at the C# code, we'll find exact implementation of this logic. We have if statement, we check that our input parameter is an SQL expression dot condition, then we cast it and store it somewhere just for the future use. In Nemerle we declare what we need, and the compiler does everything else. In C# we have to write the same code manually. Just one identifier in Nemerle and 3 lines of code in C#. The next pattern is the not predicate. Again, we use just one identifier to define our pattern, but this situation is even worse because we need to write 1, 2, 3 letters in Nemerle. In C# we still have 3 lines of code to implement the same logic. So 3 letters in Nemerle versus 3 lines of code in C#. Next predicate, compare predicate. Same thing, we have just one identifier and very similar C# code. The last pattern is the not equal operator. This C# code implements the same logic. This line of code is almost the same as what we have here in Nemerle, we just don't use new keyword and we don't need return. So once again, in Nemerle we need 1, 2, 3, 4 identifiers to declare our logic. In C# code we need about 10 lines of the imperative code. In this example we have just one pattern, but remember before we implemented 5 patterns. Let's add another pattern into our Nemerle and C# methods and see what's going to happen in this instance. This is our first pattern, constant folding. We have just one more line in Nemerle. In C# we have, let's say, more than one line. This declaration of what we need in Nemerle. In C# we have to implement this logic manually, and we have it somewhere about there. What about the next pattern? Let's look at the next one. This is a constant folding for subtraction. In Nemerle we have just one more line again, and we have implementation of this logic in C#, and this time I added some optimizations. Look at the binary sub-pattern. If the first pattern doesn't work, if the input value doesn't match our first pattern, for example, if it's a binary expression but not summary, I think it's a good idea not to check it again for the second pattern. And I implemented this logic in my C# code. It's okay, I can do it. I have to do it because I want my application to have a good performance. But the problem is that optimizations multiply the complexity of our code. This code doesn't look bad yet, because we have only 3 patterns, 3 algorithms to optimize. Let's add other patterns. This is our multiplication by 0, multiplication by 1, and now we have kind of messy spaghetti code here. Also added some more optimizations to this code, and the major problem I have here is that I don't have just one place, one algorithm. By doing optimizations of my algorithms, I mix them all, and my algorithms are actually spread all over the code. If I need to modify them, if I need to add some new logic, I have to put a lot more effort into doing that. The Nemerle compiler performs the same optimizations, so I don't have to care of them. I can concentrate on my logic, on my algorithms. In Nemerle, I just need to add one more pattern to implement one more algorithm, and the compiler will do everything else. In C# I have to go through all my code and to find an appropriate place, maybe even a few places that I need to modify. I have to be very careful, and I have to make sure that I don't break anything else when I make my changes. Even if I have unit tests, they save me from breaking my algorithms, but they don't save me from breaking the performance of my application. I did all these things for the sake of performance, and as a result I got some overcomplicated code. And by modifying this code, I can easily break the performance. Actually, this is kind of closed circular process. I do optimizations, they multiply the complexity of my code, I lose control, I break my optimizations, and finally I have to start optimizing my code from the beginning. The Nemerle code doesn't have problems like that. In Nemerle we don't mix algorithms, we separate them, we work on each pattern independently. We added new algorithms in the Nemerle code, and it's still clear, it's readable, understandable, and it's maintainable. The C# code maintainability, I have to admit that we are going to have a catastrophic degradation of the C# code maintainability if we add more and more algorithms to this code. And by the way, this example is pretty simple. In my real application I have dozens of patterns. If I implemented all of them here using C#, I would have to write a few thousand lines of code. So if you have a data structure like this, if you have data structure that can be converted into variants, into algebraic data types, I think that the Nemerle pattern matching and algebraic data types are the best choice for you to implement your logic, your algorithms, and to control the complexity of your applications. Now you have everything you need to know about variants, about algebraic data types. Actually, now you know everything what I know about them. But we didn't finish working on pattern matching yet, because pattern matching has a few more features we need to discuss. I have prepared another example, and in this example we have different types of pattern matching. For example, we have literal matching here. We can match numbers, we can match integers, also we can match doubles. We can match strings, we can match characters, and we can match enumerations. We have tuple pattern here. You remember we can match multiple values at the same time, we can match tuples. Actually it's the same things, just syntactical sugar. We can match variants. We can match really complicated data structures, we can use recursive patterns, and so on. So far we know what all these things are. Also we have list matching here, and now we are going to talk about lists. List is a type that came from functional programming. The best part about this data type is that this type is immutable. When we add a new item to a list, we don't modify an existing object, we create a new one. Nemerle has a native support for lists, and if I need to add new item to a list, I have to use this syntax. Let's create a new variable. This is my new item, and this is my existing list. If I need to add two items, I use very similar syntax, something like that. So when I add new items, I create new objects. My original object is still the same. I initialized my list with 2 items, and now I can use pattern matching to analyze this list, and if I do this, I will find that I still have 2 items in my original list. To analyze lists, we can use these patterns. For example, this pattern means that we expect a list that has 2 items, and the first item should be 1 and the second item 0. In this case, we check that we have a list of 2 items again, and the first item is 1, but we don't check what is the second item. In this case, we don't check what is the first item, and the second item should be 0. In this example, we check that our list has to have at least 1 item, and this item should be 1. And then we have the rest of our list, and we don't care what is this. If we look at the type of this item, we'll find that this is an integer. If we introduce new variable for the end of our list, for the tail of our list, we'll find that this type is a list of integers. So that's the way to decompose our list, and now we can have head and tail separately, so we can use them in our algorithms. This pattern means that our list has to have at least 2 items, and the second item should be 0. This pattern means that we expect an empty list. So this is empty list pattern. Patterns are recursive, and of course our list pattern can be part of a bigger pattern. For example, in this line we specify that we expect a function, and the name of this function is length. But we don't specify parameters, we just ignore them. If we need to tell the compiler that we expect an empty list of parameters, we can do it in this way. If we need a 1 parameter, okay, we can use wildcard to tell the compiler that we expect a list with 1 item, or 2 items, or 3 items. If we want to specify a type of our parameter, we can do it in this way. Or more details, let's add more details. We expect constant, which is string, and of course we can bind a variable and we can get the value of this string. You remember we implemented a few algorithms to optimize our SQL, and now, for example, we are about to implement inlining of the length function. We know that algorithm of this function is it just computes the length of the string, and if we have a constant string, we can implement this algorithm. We can compute the length of the string before we generate our SQL. So let's do it. Okay, it looks like I got carried off track, so let's get back to pattern matching, and our next type of pattern is the type check. We have an object here, and let's say we need to check the actual type of our object. We use this syntax to check a type, and at the same time we check the type, we cast our variable to the type we check, and we bind new value we just cast to this variable. You see the type of this variable is integer, so it's ready to be used in our computation branch. The type of this variable is string, and again we check that this is string, we cast it to string, and we bind the value to this variable. So very easy. Next pattern is the record pattern. Let me explain you what it is. Let's go to our function option. This option has 2 fields, name and parameters. You remember the compiler automatically creates a constructor for the fields. Also, the compiler associates these fields with parameters of pattern matching expression. For example, before we use this syntax to match our options, something like that. And it means that our option has 2 fields, and we have to specify both of them, or we can use wildcard if we don't want to specify one of the fields. But the idea is that we have here exact association. We don't use names of our fields, we use positions, and that's why we have to specify parameters for all of them. Actually, the record pattern is an alternative when we specify names of the fields. So we can change order of the parameters and we don't have to specify all of them in a pattern matching expression. Previous version of the Nemerle compiler supported only this syntax. The latest version doesn't require the where keyword, so we can use this simplified syntax, but anyway, all these three patterns are the same. Regular type matching. We know that the compiler needs variant information to associate option fields with parameters of pattern matching expression. But we have an alternative syntax when we use names of our option fields, so we can use the same syntax to match irregular types. In this example, we have system.link.expressions. Actually, link expressions as a data structure is very similar to variants. We have one abstract class, which is expression, and a bunch of inheritors. So, using regular type matching, we can manipulate this data structure almost in the same way we manipulate variants. And the next question is, if the compiler automatically associates option fields with pattern matching expression parameters when we define options, is it possible to define the same associations for irregular types? Yes, it is. We have a marker extension pattern that allows defining such associations. This marker has two parameters. The first parameter is a base class, in our case this is expression. The second parameter is a pattern expression signature, how we would like to see it in our match operator. For example, we want to use it in this way. Okay, so this is a signature, and then we have a real pattern that will be used by the compiler instead of this signature. So we can use this assembly level marker attribute to define pattern expression signatures for the whole expression hierarchy, and then this hierarchy will look almost exactly like a variant. Okay. Well, we're almost done. Just one more feature that I want to demonstrate. This is a short version of the match operator. Sometimes we need to check that this f variable is a function. So we want to check this pattern. We don't need to match anything else, just this condition. In this case, we can use this syntax. It returns a boolean, and we check that this pattern works. Of course, we can use it as a part of other language constructions. For example, let's use it with the when marker. Okay, we can use it in this way, and even we can bind some variables, and then they are available in the when marker body. Okay, something like that.
Okay, we are done. Now you know everything I know about pattern matching and algebraic data types. If you have any questions, comments, concerns, please visit my blog where we can discuss pattern matching, algebraic data types, Nemerle, and everything else.